Okay, so hi everyone. My name's Jen. I did my ROBO master's thesis on event-based vision for high resolution microscopy imaging. So basically, what I'm going to be talking about today, kind of a bit of a table of contents. First, I'm going to talk about kind of the background and theory. So what even is conventional microscopy? Why is it bad? Or why can we improve it? What exactly is event-based vision and how can it potentially help? Methods in terms of experimental design. How am I going to prove that event-based vision is better for microscopy? And then sort of go over my results, and then finally my conclusion. So BLUF stands for bottom line up front. Event-based cameras, as I discovered during this thesis, have a better spatial resolution than frame-based normal cameras for microscopy. So why exactly is this? I'll start with a little bit of background on traditional microscopy. Basically, the big problem we have is that normal microscopes are limited in their resolution, so their ability to image things, by the diffraction limit. So kind of a proof of concept. If you look at this particular image, it looks like it could, we know it's a car on a street, but the thing is, you can't really tell if it's really one headlight or two different headlights because they just, they're so close together, and the way that light diffracts kind of shows that kind of overlap. And then as it gets closer, you can see that, okay, well, now this is two separate headlights. And then finally, as it gets even closer, you can tell that, oh yeah, they're two separate objects. So this is known as the diffraction limit. The diffraction is basically just the bending of light around / through an obstacle. And what this does, at least in microscopy, is that as the light bends around the objective of the lens, instead of actually showing the object itself, you find that there's an object, and then there's like rings, concentric rings of light around it. And there's math that you can, like the Rayleigh limit shown here is you can compute exactly the radius of the smallest ring of these sorts. It's called an Airy ring. And basically the way that the big thing that determines this, as you see, like the NA, what exactly is NA? Well, that's numerical aperture. And for a microscope, the numerical aperture is essentially just how well the microscope can concentrate the light that is being used to image the item. So the better way to think about it is how wide is the cone of light we're seeing. So if you look on the bottom left, you see that a lower NA means that you have a skinnier cone versus a wider, like a higher NA results in a wider cone. And you see that the higher the NA is, the smaller the radius is. We want a smaller radius because that shows that the light doesn't diffract as much. You can get a clearer view of the image you're actually seeing. So, well, this becomes an issue when these rings start overlapping in a microscope. So if you look, phi over here that I'm circling, I don't know how well you can see it, is essentially just the angular separation between two objects. So kind of explaining what's going on in this diagram, here's the objective of the microscope lens. And here's the actual location of these two dots. So there's a dot right here and there's a dot right here. This is what's projected back to our eyeballs or to an image or a camera or whatever it is. And you can see that when phi is large enough, the way that these, the angular separation allows for you to see like two disparate objects. However, when phi gets too small and they're located too close together, these Airy rings start overlapping and it starts looking like one blob instead of two separate ones. So what exactly is diffraction in conventional microscopy? Well, some way to reduce, when we're faced with this diffraction limit, what we want to do is reduce the resolvable distance. There's a couple ways to do this. You can either decrease the wavelength of light. So a lot of people will use like UV light, and that's another, like UV light microscopy is a thing, or increasing the diameter of the objective lens. And this is what you see in telescopes, where they have meters and meters long, wide objective lenses to be able to have better resolution when you're imaging stuff. However, it's not super applicable, or you're not really able to get a meters long objective to, I don't know, it would be hard to fit in the lab, is kind of one way to put it. And additionally, as we've seen with conventional light microscopy, our diffraction limit is roughly 250 nanometers, even with the widest objective, the best wavelength, the best conditions, we hit a pretty hard wall at 250. And breaking this limit requires X-rays, which are incredibly difficult to build, like the optical framework to use. Never mind the fact that they're pretty dangerous to humans too. So whether we've turned to other methods of microscopy in order to show like higher resolution imaging to break this 250 nanometer. Two different ways are the electron microscopy and super resolution microscopy. These essentially take advantage of how electrons have a shorter wavelength of light to produce a better image. However, there's a lot of downsides. First of all, incredibly expensive. You have to buy all this equipment. And you also require a lot of sample preparation. So like slicing the sample so it's a certain amount of thickness, or oftentimes you have to dye them to show like fluorescence and stuff. And so basically, okay, well, we're looking for more applicable, cheaper alternatives to conventional microscopy and also to these high resolution imaging methods, which aren't always feasible. So this is where event-based vision comes into play. I'm just gonna right here go over, all right, so what exactly is event-based vision? I know some of you are familiar with it, but I'm not sure, so I'm just gonna go through it. First, to really know how event-based vision works, I'm just going to go over like how exactly a normal camera works. So normal cameras use a shutter, which means that at a specific timestamp, they only capture data at that particular time. This means that each image, the result of this is an output of, say, like an array that's the size of the pixel view field, as you see kind of on the bottom right over here. And each array element contains the magnitude of light intensity in it. So like at this pixel, let's say it's like 100, and at this pixel, it's 95 or something like that. And a video is essentially just a series of these frames. And this provides a lot of redundant information, especially if that part of the picture doesn't change from time to time. So why am I recording over and over again something that I already know? And it provides a lot of redundant information. So event-based vision is kind of an alternative to this. Instead of actually measuring the intensity and magnitude of light, you only capture the change in the brightness that you have. And this is often called neuromorphic vision, in that it kind of models the way that our brains work. In that we have it honestly follows the general model of neural computation and learning that our retinas use. So for example, here you see like there's a model, and the model is per se like our retina. So what our eye captures as like, this is the brightness at that particular pixel, at that particular point in our view field. And then we get an input from outside saying like, oh, well, I thought like my model says it's 100 at this particular pixel, but the input says it's actually 150, so it got brighter. So you compare the two, and because the output says, oh wait, actually it got brighter, then now you have to modify your model to say, oh wait, actually, okay, fine, we understand, it's actually 150 now, not 100. So that's kind of this like neural computation loop that event-based vision is based off of. So basically the entire point of an event camera is capturing these events of where you change this model. So event is just a change in brightness at a certain pixel. Brightness is a very loose term, but in here, what we mean is it's the log of light intensity. So kind of explaining this equation over here. So the change in brightness at position X comma Y at timestamp whatever, is equal to the polarity, which means that, okay, did the light turn from dark to light or light to dark, times the threshold C. So an event is triggered only when you have a certain, like the light changes by a certain threshold, because obviously depending on how big or small this threshold is, that determines exactly how like the noisiness level of your image. So basically what this means is instead of getting a frame of a particular array size, you're going to get a continuous stream of information that's, okay, at this timestamp, at this location, that pixel went from light to dark. And then immediately followed by, okay, well, now at this timestamp at this location, it went from dark to light. And you just get a continuous stream of events. So it doesn't really look like your typical image. Some benefits of this is because you're continuously getting this information, you have a very high temporal resolution in the microsecond range. And that also means low latency because you don't have to worry about, you pretty much get your information right as it comes in. And this also shows like an improved dynamic range because we're only capturing the change in light instead of the actual magnitude of light. You can capture a far wider range of intensities. There's so much less overhead because you're not repeating redundant information as well. So how does this look like in practice? So in order to, when I started my experimentation, I ran a little bit of calibration testing on the event camera I had. I drew a little diagram. So this is the event camera. I hooked it up directly to an LED light source that I hooked up to a function generator that I set it to an exponential rise function. So when you have an exponential rise function, since the events are only captured at log intensity, I should presumably get an approximately linear series of events because you have exponents and then take the log of it. So it results in a linear chain. And that, as you can see kind of on the right, these blue dots are the events. And this yellow-orange line is the actual function that is being modeled through the LED's brightness. And you can kind of see that, yeah, it's approximately linear in the time scale. You see that there's a bunch of events at the very beginning and then they space out a lot towards the end, which we're presuming this is expected because of that, like log reduces the magnitude a lot. And I got approximately the threshold for this like log change in brightness is approximately 0.3. So, okay. Now that we got that out of the way, how am I going to use this event camera for microscopy? So kind of bringing it back to the beginning, my goal through this project is to show that the event camera has a better resolution than the frame-based camera for microscopy. And how exactly am I going to do this? Well, I'm going to image the same exact sample using both cameras and see which one performs better. So, well, something to note here is that the event camera requires movement of some sense. And a static microscope doesn't really give that to you. So in order to do this, so how am I going to introduce movement? And we decide to do this by changing the focus of the image. So as you bring, if you've imaged something through a microscope, you can see that at first it's out of focus, and then you mess with the focus a little, and then it comes sharply, and then it goes blurry again. So I take advantage of this change in the focal stack to kind of introduce movement and edges to what's going on. And we did this by using a piezoelectric scanner. This is a tiny, like a motorized scanner that you attach to the objective that moves the objective like closer or farther away from the sample itself. And I hooked it up to a ramp wave. So essentially it just linearly moves up and down at a very, I think I put it like the period is 5 seconds. So that's like a 200 millihertz ramp wave right there. And then kind of the experimental design. This is the Nikon inverted microscope that I used. Down here is the objective with the objective scanner. I put the sample up on the stage, and here's the event camera hooked up to it. So the actual image that we're going to be using is this resolution test image, which is commonly used for calibrating microscopes, because you can see all of these lines. It's a very standard set of lines, and you can look, they have it online, like there's a specific width of each of these lines that you can match up to. So you like know the resolution of whatever microscope you're using to image using this test sample. So, okay, well, what are the results of all of my testing? And first, in order to do that, I have to kind of talk about, well, how am I going to take this stream of events and turn it into an actual image? And the dumbest way of doing this is by binning these frames. And essentially, I just group events by timestamp. So take this continuous stream of events, and I say, all right, well, I'm going to group them by groups of 100 milliseconds. And I basically take everything in that 100 milliseconds and I plot all of those events to create like a crude 2D image type of thing. And actually, this worked really well, really well. if you can see, it's not super visible, but in frame 9 is the in focus frame. That's where we get the most granular imaging. And then it so it gets blurry, it comes into focus, then comes back out of focus. And the nice thing is that, okay, it's a really simple method. You can get a pretty clear image, but the cons of this is it's 2D. So there's no really depth to this image. The less dumb method is to use a cumulative sum. So essentially, let's take it back to what exactly is an event. Well, an event is just the change in brightness. So the change in brightness, also known as the derivative of brightness. If you take the derivative of brightness, then you get, if you take the integral of this derivative, then you're left with the absolute magnitude of brightness that you actually have. It's not perfect, of course, there's a lot of math going on behind it, but essentially a cumulative sum is if you start at time 0 up to event K, well, the pixel's value, instead of just that particular event and you plot it, it's the sum of all the previous events up to that point. And that kind of gives this more absolute brightness scale instead of just an event. You can kind of see it gives a little bit more depth to the image. It looks a little bit more 3D, so that is pretty good, better than the previous method. And the less dumb method from the cumulative sum is the symmetric sum. So the issue with the cumulative sum is that it only captures information from time 0 to that particular event K. However, the symmetric sum, okay, so the first part of this equation is the same. You get it from, okay, the first Z position to your K, add up all of those. But then after that, you add the inverse of all of the following events. So the benefit of this is that you get a look at the entire focal stack instead of just from 0 to K. And you can kind of get a better image of what's going on. So, okay, fine. Now let's talk about the actual, how did this do in comparison to the CCD? So on the left, you see the CCD camera's image, and on the right, you see the event camera's image. The reason that they're flipped is because it's an inverted camera, and the Nikon already flips it back for you. They're the exact same image, just put on 2 different cameras. And if you look, this is the smallest set, this is the smallest test pattern on the resolution test. And you can see that where there's just a blurry blob on the CCD camera. However, on the event camera, you can see that same exact point. There are 3 very distinct lines like there are supposed to be on the resolution test image. So that's just a visual proof of concept. But now I'm going to show you how it works in terms of the math. So the frame-based camera, when you use the Rayleigh resolution calculation method, you can see that the diffraction limit is 2.81 microns. However, the smallest test image there is actually 2.2 microns. This tiny line here is actually 2.2 microns in width. Actually a little less, it's 2.19, but microns are so small. And anyway, basically this diffraction limit says points closer than this 2.815 cannot be resolved. However, on the event camera, the pixel resolution itself, so each pixel is 2.2 microns a pixel. And I use the Fourier transform as a method to kind of see, okay, what's the highest wavelength of light I can image using this? And I was able to show that, okay, it's around 2.2 microns a pixel. So the smallest image, 2.2 is obviously smaller than 2.81. So the event camera was able to do better than the frame-based camera through the math as well. Okay, well, so now my conclusion. So event cameras are better, but now what? So event cameras are able to pass this conventional diffraction limit that limits frame-based cameras and conventional microscopy. And I think it's because we don't capture the actual magnitude of the intensity, and we capture just its change. So as this temporal, it changes, it goes in and out of focus, we're able to actually capture more granular details because we don't see, because we're not using the conventional, just capture the intensity at that particular point. And basically, through the math and through the visual that I showed a couple slides ago, you can see that the event camera is better able to show 2.2 is indeed smaller than 2.8. So kind of some discussion about what's going on, thoughts for future things. A longer exposure time is better. So I showed that there is I the ramp wave is 200 millihertz. So there's definitely a trade-off in terms of like spatial resolution and temporal resolution. So how fast can we image these? Not that fast if we want to get all of the details and all the granularity. So that's kind of an issue. There's also a lot of calibration required as where it is right now. You need to determine exactly what's the best Z sweep range, how noisy you want the camera, how many events you want it to detect. I mean, also like in post-processing, determining like the size of the frame groupings, like where exactly, like which frame is the one that's in focus. And right now I have to do all of this by hand, which is not the best. Additionally, I noticed that this particular image is limited by the pixel size of the particular camera that I'm using. Like because the smallest image is literally the size of 1 pixel. So I cannot image anything smaller than 1 pixel. And future work in this could be to use like a different, an objective with a different magnification or a different NA for help with that. And then kind of the future potential, like this is a very basic proof of concept, but in the future, it would be cool to break the 250 nanometer diffraction barrier. And additionally, there's a lot of potential for dynamic imaging. So if you look at these two images, this is a silica. I actually took this at the very beginning just to see like, oh, like, let's see how it does with a moving thing. So this is a silica particle moving around in water and in solution. And you can see that you can pretty much, you can track the way that it's moving depending on like, okay, these are the rising edges, these are the falling edges. And you can see that like, okay, these are falling edges, these are rising. So the silica is like moving kind of downwards here. And that a lot more needs to be done in order to actually figure this out. But there's a lot of potential for dynamic imaging with this event-based vision method for microscopy. That's all I have. Thank you very much. I'll take any questions.
Great, thank you. Give Jen a round of applause. And I'm opening the floor for questions. Feel free to unmute or, type your question in the chat. So I have a question for you. In your silica experiments, so how did you get them to move, or did they just kind of float around? And
yeah, I mean, because it's in water, it's exhibiting Brownian motion, so it kind of just wiggles a little bit. And then I was like, oh, well, I can see Brownian motion using an event camera, which is kind of cool.
That's pretty neat. And so then the question, I guess, in my follow-up question in that case is the fact that, how do you, what's the timing? Because you were talking about there's this trade-off, right, between time and space. And so how, in terms of the dynamic imaging side of things, how much do you have a sense of like how much motion is detectable, and for the given sensor, those kinds of parameters?
Well, the event camera, like the base is in the microsecond range. It can detect in that. That's what the event camera spits out in terms of. It really depends on how detailed you want the image to be. With the silica, it's literally a circle. So I'm like, all right, I could literally take 3 events and be like, oh, the silica is moving in terms of like centroid estimation, but it probably would not get in the microsecond range if I wanted to like actually really well image what's going on. Okay.
That's very interesting. People who do particle image velocimetry, right? So this is in the fluids community. I never quite understood this, but they talk about sub-pixel resolution, and there's math involved. But it's a really, I mean, this in some ways is kind of related, right? And I think it's actually pretty interesting trying to understand, when you sweep, right, when you take things in and out of focus, but then how do you, if you're doing dynamic imaging, how does that, be interesting to do a detailed study of how, one maps those kinds of changes to timing and motion and rates of change and things like that. So this is really cool stuff. Any other questions from the audience? Okay, let's give Jen a final thank you.